Hi everyone, I'm Saujanya Ponnapalli from UT Austin. I'll be presenting our work RainBlock that proposes a new architecture for public blockchains. This is joint work with VMware Research and Novi and DM Financial. Blockchains are decentralized databases. In blockchains, servers executing transactions are called miners. Each miner stores a chain of blocks which maintain the history of processed transactions. Each block stores an ordered list of transactions, and any block is processed only after its previous block. Public blockchains have open networks, so they allow any server to execute transactions. This means at times miners can be malicious. So public blockchains like Ethereum employ consensus protocols like proof of work. With proof of work, miners compete to create the next block. Once a miner creates a new block, it sends the block to other miners. Other miners first verify the block, then process its transactions, and finally accept or reject the block. Only after most of the miners accept or reject the block, proof of work allows the creation of the next block. This way, proof of work rate limits the creation of new blocks for the safety and security of the blockchain. Two of the most popular public blockchains, Bitcoin and Ethereum, use proof of work consensus and suffer from low throughputs. While Bitcoin can process 20 transactions per second, Ethereum processes around 16 transactions per second. However, centralized transaction processing engines like Visa process more than 20,000 transactions per second. So clearly, public blockchains need to achieve better throughputs for enabling mainstream decentralized applications. Prior work proposed modifying proof of work or using new consensus protocols for better performance. For example, Inclusive Blockchain Protocols and Bitcoin NG proposed modifying proof of work, while Algorand proposed replacing proof of work with a faster alternative like proof of stake. Orthogonal to these efforts, we attempt to see if we can increase the throughput of public blockchains without modifying proof of work consensus. Using proof of work unmodified allows us to inherit its safety and security properties. To find an answer to this question, we look at how miners execute transactions and create new blocks. With proof of work, Ethereum miners have about 10 to 12 seconds of time to process transactions and to generate a new block. Ethereum miners use two sets of threads, workers and sealers, to perform these operations in a pipeline manner, which I will describe now. Workers first process transactions into a partial block. To process or execute these transactions, workers must read, modify, and update the system state on disk. So workers must perform I/O for processing transactions. Workers then send these partial blocks to the sealers. Sealers solve the proof of work puzzle to generate a new block. While the sealer is generating a new block, workers process the next set of transactions for the sealers. We observe that if workers can process more transactions in the same amount of time, then sealers will be able to generate larger blocks. Note that the network latency in propagating a slightly larger block is not the dominant cost. Ethereum has increased its block size several times previously without increasing the block propagation latency significantly. From our analysis, we see that although proof of work rate limits the creation of new blocks, it does not limit the number of transactions in each block. Our analysis also highlights that it is the I/O bottlenecks that limit the block size and thereby reduce the overall throughput in public blockchains. I will now empirically show the impact of these I/O bottlenecks on the overall throughput. For this, we run a micro benchmark using two private Ethereum clusters, each with 3 miners. While the first cluster has no system state, the second cluster is initialized with 10 million user accounts. Both these clusters process 30,000 transactions in total. Despite using the same proof of work consensus, the second cluster has 6 times lower throughput and creates blocks that are 2.5 times smaller than the first cluster. We measure that miners in the second cluster spend 60% of their time performing I/O operations. Therefore, we establish that I/O bottlenecks limit the number of transactions in each block and thereby limit the overall throughput of public blockchains. So the central idea of our work is to make transaction processing faster to increase the throughput of public blockchains. Our goal is to help miners process more transactions in the same amount of time. This can be achieved by reducing the I/O bottlenecks in transaction processing and allowing miners to safely release larger blocks. So with these insights, we propose RainBlock, a new architecture for public blockchains that increases the overall throughput without modifying proof of work consensus. RainBlock achieves higher throughput by eliminating the I/O bottlenecks in transaction processing and allowing miners to process more transactions in the same amount of time. For eliminating I/O bottlenecks, RainBlock uses the novel distributed sharded Merkle tree or the DSM tree data structure to store the system state. In a geo-distributed setting, RainBlock miners can process about 20,000 transactions per second. First, let's look at how transactions are processed in Ethereum. Ethereum miners store the system state locally on SSDs. To execute a transaction, a miner first reads the necessary data from the SSD into DRAM. It then executes the transaction and modifies the data accordingly. Miner then writes the changes back to its local storage. Once the miner mines this transaction into a block, it sends the block to other miners. Other miners also read the data from their local storage, execute the transactions in the block, and modify their state accordingly. This way, miners re-execute transactions to ensure correctness. Zooming into how system state is stored at each miner, the state is stored using authenticated data structures like Merkle trees. Merkle trees provide data along with proofs that help verify the correctness of the data. The system state in Ethereum is stored in a logical Merkle tree, which is flattened and stored as key value pairs on disk. Traversing such a tree requires multiple random disk reads, and updating a value results in multiple disk writes. We measure that to read a single user account, Ethereum miners read 40 to 60 times more data. And to process a single block of 100 simple transactions, Ethereum miners perform 100 times more random I/O operations. In the rest of today's talk, I will first describe RainBlock's architecture at a high level and discuss how it overcomes these I/O bottlenecks. I will then detail two main challenges that RainBlock solves to achieve better throughput. Finally, adding more details, I will walk through the life of a transaction in RainBlock. In RainBlock, the system state is decoupled from miners. It is sharded and stored across the memory of multiple storage nodes. These nodes store the Merkle tree in a memory-optimized format using the DSM tree data structure. I/O helpers are introduced to perform I/O on behalf of the miners. Typically, I/O helpers prefetch the data required for executing a transaction from the storage nodes. I/O helpers then submit the transactions and the prefetched data to the miners. Miners execute the transactions, create a new block, and update the storage nodes. Storage nodes perform these updates asynchronously. Thus, miners in RainBlock process transactions faster, typically without having to perform any I/O in the critical path. RainBlock needs to address two main challenges before it can achieve high throughput. In RainBlock, I/O helpers can prefetch data from storage nodes while miners are updating them in parallel. Therefore, storage nodes need to provide consistency in the presence of concurrent updates. Secondly, RainBlock architecture trades off local disk I/O for network I/O. So RainBlock needs to reduce the amount of data transmitted over network. Note that the stateless client's proposal from Ethereum introduced separate storage nodes, but it did not gain traction due to its high network overheads. Recall that in RainBlock, I/O helpers can prefetch from storage nodes while miners are updating them in parallel. Further, as miners share the storage nodes, multiple miners can update them simultaneously. To handle this, DSM tree in storage nodes employs copy on write. On updates, storage nodes create new copies of the modified data. Similarly, IO helpers prefetch data from a specific snapshot or the latest snapshot by default. Once blocks in the main chain are confirmed, snapshots from unconfirmed blocks are garbage collected at the storage nodes. Naively, IO helpers may prefetch full paths in the Merkle tree called witnesses and submit them to miners. However, RainBlock miners store the top layer of the DSM tree in a private in-memory cache. The two layers of the DSM tree, the private top layer at the miners and the common sharded bottom layer in the storage nodes, collaborate with each other to reduce network traffic. For example, miners can store the top layer of the DSM tree till a configurable depth. IO helpers, instead of fetching full paths, can prefetch only data that is not present at the miners called compact witnesses and submit compact witnesses to these miners. Such cross-layer optimizations in DSM trees reduce the network traffic in RainBlock by up to 95%. In summary, RainBlock miners store the top layer of the DSM tree while the bottom layer is sharded and stored across the memory of multiple storage nodes. IO helpers pre-execute transactions to prefetch compact witnesses from storage nodes. IO helpers then submit the transactions and the compact witnesses to the miners. Miners use these compact witnesses and their private cache to process transactions. Miners then create a valid block and update the storage nodes. Storage nodes asynchronously create new snapshots of data corresponding to the updates from the new block. Old, unconfirmed snapshots are periodically garbage collected at the storage nodes. In RainBlock, all components, storage nodes, IO helpers, and miners work without trusting each other. As RainBlock uses proof of work without any modifications, it has the same safety and security properties as Ethereum. RainBlock's architecture sure adds complexity, however, it is in return for much higher throughput and better scalability. For details on RainBlock, please find the full paper online. To evaluate RainBlock, we use Amazon EC2 large instances, each with 32 gigabytes of DRAM and 48 threads. Storage nodes, miners, and IO helpers are deployed on their own instances. We use a workload generator to synthesize workloads that are similar to the transactions in the public Ethereum mainnet. We notice that a single Ethereum miner can process 1,000 transactions per second using a single server for hosting the miner. This is the best case scenario for Ethereum, and we compare RainBlock against this baseline. Note that the publicly available numbers for geo-distributed Ethereum show that it can process about 16 transactions per second despite using more than 4,000 high-end servers. A single RainBlock miner with one IO helper and 16 storage nodes can process more than 2,000 transactions per second using a total of 18 servers. By using 4 IO helpers instead of 1 IO helper per miner, we increase the amount of data prefetched and submitted to RainBlock miners. In this setting, a single RainBlock miner can now process more than 7,000 transactions per second using a total of 21 servers. Using the same number of IO helpers per miner, but after introducing the DSM tree cross-layer optimizations, a single RainBlock miner can now process more than 27,000 transactions per second using the same 21 servers. Finally, in a geo-distributed setting, RainBlock uses 4 miners that are in 4 different regions spread across 3 continents. Each RainBlock miner has 4 IO helpers. In this setting, RainBlock can process about 20,000 transactions per second using a total of 32 servers. We noticed that the throughput was stable even with a higher number of miners. Overall, RainBlock shows how a small percentage of extra hardware can be used to improve the performance by orders of magnitude. In summary, RainBlock builds on the main insight that I/O bottlenecks limit the block size and not proof of work consensus. It avoids I/O in the critical path of processing transactions at miners by introducing I/O helpers and storage nodes. RainBlock uses DSM trees to reduce network traffic and can process about 20,000 transactions per second in a geo-distributed setting. Thanks a lot for tuning in for this talk. I'd like to extend a special word of thanks to my longtime mentors, collaborators, and my advisor for making this work possible. Please check out RainBlock on GitHub and reach out to me with any questions, comments, or feedback. Thank you.